Hello, my name is Dan Brunner, and today I will be going through how to solve problem 1.52 from Chapter 1 in the Fundamentals of Mass and Heat Transfer textbook. So looking at our problem statement, we're told that we have a photovoltaic panel that is 2 by 4 meters installed on the roof of a home. This panel is irradiated with a constant solar flux of 700 watts per square meter. The absorptivity of the panel is 0.83, and we're trying to find the electric power that is generated by the panel. We're given this efficiency of electric power generation, which is a function of the panel temperature. And so we're supposed to find this power generation on a still summer day where there's a higher temperature and higher ambient temperature and a lower convection coefficient. And then we're also supposed to find the power generation on a breezy winter day where there is a lower ambient temperature and a higher convection coefficient. Another important thing to note is that the panel emissivity is 0.9. So writing down all that was given in the problem, we have our length and width, which together we can use to find the area of the solar panel. We have the constant solar flux, we have the absorptivity, we have this efficiency of electric power generation, which again is a function of the panel temperature. We have the emissivity, and of course, we have the Stefan-Boltzmann constant, which will be important when we calculate the rate of radiation heat transfer. So an important thing to note is that in the picture I've drawn here, my heat transfer rates are drawn from the panel to the surroundings. And so that'll be important for when we write the equations for making sure that our signs are correct. So again, we're asked to find the power generation um, uh, with two different sets of conditions. And because the power generation is a function of the panel temperature, that quantity is essentially what we're trying to find. And so to help us find the panel temperature, we need to make some assumptions. The first being that the panel has reached steady state conditions. There are no time varying changes to any of the variables, including the temperature. The panel is a small object in a large enclosure. This is an important assumption for when we're calculating the radiation heat transfer rate. We have constant and uniform convection and radiation. We're not considering any conduction away from the panel to the roof. Um, there is no heat generation in the panel, and we're assuming that the panel surface is isothermal. So the temperature is constant everywhere on the surface of the panel. The governing equations that we'll be using for this problem include the heat transfer rate due to convection, radiation, and absorbed radiation. We'll be using the first law of thermodynamics, and we'll perform a closed system energy balance. And we also have this power generation rate equation, which is, um, again, a function of the panel temperature. So based on the assumptions that we made, we can cancel out, well, effectively cross out the stored energy term. Again, you might remember that that term is equal to the mass. If we're talking about sensible stored energy, that term is equal to the mass times the specific heat times the time derivative of temperature. And so because the temperature is not varying with time, that time derivative term goes to zero. And we're also canceling out the energy generation term because the panel is not uh, producing any power within itself. And so when we make those assumptions and simplify our governing equation, our first law of thermodynamics, we get that the absorbed radiation heat transfer rate is equal to the convection heat transfer rate plus the radiation heat transfer rate. And when we plug in the formulas for each of those three separate terms, we end up with this equation on the bottom, where we have our panel temperature raised to the power of 4 plus the panel temperature again. And so this equation right here must be numerically solved. Um, and so to do that, what I did, there are, I'm sure, several different methods to go about this, but I made a MATLAB code, um, and I used a first order Taylor series approximation to iteratively go through and eventually get a better and better guess for the panel temperature. And how this works is once the panel temperature reaches a value that satisfies the function condition, the function itself must equal one, based on how it's rearranged. Once that condition is satisfied to a satisfactory degree, there's a tolerance factor that you have to include. The loop will stop and you'll have your final value for the panel temperature. Of course, this is just an approximation, um, but I have a MATLAB code that I can show you. And so what I did here is basically just that. So I initialized all of the constants for each of the two scenarios that were given. The tolerance that I used was 1 times 10 to the negative ninth. It's a very small tolerance. You can use whatever you want, and the value will be less and less accurate the higher your tolerance is. Um, or I should say, the larger your tolerance is. And so I rearranged the equation to create this uh, panel temperature function. I took the time derivative of that panel temperature function, and then using the first order Taylor series approximation, I went through and iteratively calculated a new guess for the panel temperature. And eventually that produces values, or a value of the panel temperature that is satisfactory. So if I go ahead and run this code, uh, let me rename this real quick. Just take out the problem number. So I go through and run that, and you can see that um, my panel temperature and power generation is output is produced, for both the first and second scenarios. And so the temperature of the panel in the first scenario on the still summer day is 342 Kelvin, um, which is around 150 degrees Fahrenheit. The associated power generation is 980 watts. And then for the second scenario, where we have a breezy winter day, the panel temperature is lower, substantially lower. It's calculated to be 275 Kelvin, and the associated power generation is 1,291 watts per. Sorry, just watts. And so going back to the slides, um, here are the answers for the panel temperature. Again, the power generation, and that is how you go through and solve problem 1.52.